We might watch this more later. Apologies for. We'll watch this later, and it'll be a little bit more meaningful. But for now, it's, I guess, something to get in the mood. So first we're going to talk about the tautological line bundle. Gamma 1 over CP1. And then we're going to look at the associated sphere bundle, which is the Hopf bundle. And the bundle map in the Hopf bundle is called the Hump Map. And that's actually, just as a map between spaces, probably one of the most famous maps, arguably the most famous map in algebraic topology. So, but we're going to start with, if you will, just verifying one of the axioms for Chern classes. So we're going to consider, this is CP1, which we can think of as the space of lines, and C2, or if you want, one-dimensional subspaces of C2, which are complex. And the way we're going to think about that is using homogeneous coordinates. So we've got Z1, Z2, and when I write them in these brackets, that means that pair is equivalent to the pair where I scalar multiply both of them by the same number, because that's what happens if you're looking at a line. And what I want is that I don't allow 0, 0 among these, and I don't allow 0 among the lambdas. And if I want, optional, I get the same space if I restrict to those where these are on the unit sphere for the complex numbers. That would be the 3 sphere. And lambda is also a unit number, which means that lambda bar is 1. So that's explicitly in coordinates how we're going to deal with CP1. You could also, right, this is also called C hat, and it's homeomorphic to S2. So a good old friend S2, but thinking about this in this particular complex way, simple way, and using the complex numbers. And then you've got your gamma 1C, where you're going to look at pairs of a line, and then all of the scalar, all of the points in C2 on that line. So a line in C2 and any point on that line. So I'm going to think of this as, oops. Okay, so we've got this inside CP1 cross C2. Okay. And then what is our recipe for a section? It's project E1, so it's the projection onto each line in CP1 to get a vector in that line, in other words, an element of this, the total space of this bundle, and it's a projection of this vector, 1, 0. and onto each line. So that's the recipe that we've been giving. And well, what do you mean by projection? It's orthogonal. It's really unitary projection, if you will. Sometimes you still see people call that orthogonal. That's fine. But explicitly, what is it going to do? So it's going to send Z1, Z2 with, say, we're going to use this we're going to send Z1, Z2. What is the value of the section? It's going to be Z1 bar. When I project, you might think the projection of 1, 0 is just Z1. That's true. That's a formula in the real case. The projection in this case is Z1 bar times that particular choice that I've given for the equivalence class Z1, Z2. So, so you could recall that this is unitary projection, or you can check that this is well defined. Don't really care about whether it's unitary projection, just check that we get a section. So what happens if I take lambda Z1, lambda Z2, where lambda is a unit complex number? Well, that's going to go to lambda bar Z1 bar times lambda Z1, lambda Z2, but these are equal. So this is well defined when we have that complex conjugation. That is a way to make a section. And we're going to check transversality. Well, of course, the value, so this says it's well defined. It's pretty clearly continuous then, because it's using the Z1 coordinate projection. And then the section is 0 if and only if Z1 is 0. So that's the point, 0, 1. And we really want to think of that as if we think about this as the complex numbers with a single point at infinity, this is the point 0. We were projecting, by the way, this point here, it's representative. Let's remember that 1, 0 is a point at infinity. So so we were kind of projecting from the point at infinity. That's just how it works with the conventions of slope, et cetera. And we found the 0 at 0. And yeah, so let's just go through the last bits. So that's 1, 0. And then we find that, so let's talk about transversality and orientations, and then make the calculation. What is the sign at this point? So you want to co-orient the 0 section if you want to be consistent with the geometry, with the algebraic geometry. We want to co-orient the 0 section, well, who's the normal bundle to the 0 section. Well, the normal bundle to the 0 section of a bundle, which is also always isomorphic, then to that bundle, by just in a fiber, take any vector in the fiber and then scalar multiply it by I. And again, the argument last time will say that that's consistent. we're not relying on a section. We just have to have this equivalence class of two vectors, because yes, we're doing complex geometry, but this is over the real numbers that we're making all these tome cochains calculations. And so you need two vectors to span the normal bundle, and this will consistently do it for that orientation. And we can orient 0 in C, which is sitting inside C hat or CP1, by choosing the image of the well, the tangent bundle was really C cross C, but anyways, by standard abuse, when you're looking at a sort of a bundle over a chunk of Euclidean or complex space, just list those vectors, and in that case, it's 1 plus 0i and 0 plus 1i, as you would expect. And so that means, if you think about it, when we there's a couple ways we talked about pulling back the co-orientation, but you can also take the oriented basis in this case the base of the bundle, the CP1, look at the Jacobian, their image under Jacobian, and then project them onto the normal bundle. Again, that can be either orthogonal projection if that's what you prefer, or normal bundle is just ambient tangent bundle modulo the bundle. So you just look at their images, and you find in this case that so the image of these of the the tangent space at 0 inside C hat in the tangent space of the tautological bundle restricted to just the point 0, 1 is, well, you look at how the action is up here, right? This is the key. This is our action. And 1 will, not surprisingly, go to 1, so to speak, and I will go to minus I. So you have to say a little bit more perhaps about how you're identifying the tangent space of gamma 1c over that fiber 0, 1. It's a line with slope 0 or whatever, but with the complex numbers. But yeah, and so what we find is that 1 and minus I versus what's supposed to be oriented is V and IV, they don't match. What? So in fact, this sign oops, what did I do here? C1 of gamma 1c over CP1 is minus x in H upper 2 of CP1. And that would also be true for others. So there's a minus 1. In fact, our algebraic geometry friends know all about this. They, in fact, refer to gamma 1 by the name. So gamma 1 is often referred to by this sheafy name, O minus 1, talking about somehow the sections on it or something like that. So there's a little bit of abuse, but that's what folks often call this line bundle. So a little bit of a surprise there. You know, as a topologist, you can always say, all right, well, maybe I'll just choose a different orientation, right? There's no reason to, maybe in light of this, maybe we should choose minus x as the generator for h upper 2 of the sphere or something like that. But you know, I made a big deal that if you're doing things geometrically, then the natural co-orientations and orientations, we want them to all come from complex structure, in which case this is a -1 that's here. That's part of the landscape. So let me give a second explanation of this -1. So to gamma 1c. And the point is that the way we're going to think about, so first of all, complex line bundles over CP1 are the same as oriented real plane bundles over, let's just call it S2. The point is that U1 is the same group as SO2, one of these low dimensional coincidences which lets you go back and forth. So and we're gonna think about this more as a real bundle now. And let me do a little digression over here before. The point is that we're going to trivialize this plane bundle in the north and south pole, and we're going to then think about not the overlap in the open set way that we were doing before, but just along the equator. But let me just give you a little digression. It also is an invitation to a bit of more homotopy theory here and there when you learn some of these topics, if you haven't yet. In general, whatever kind of bundle I'm looking at, n-dimensional bundles, when I'm looking at a space that's a suspension, so here's a suspension, well, it's made of two cones. The bundle is trivial over the cone, and each cone, and then I just need to glue it along the middle. So that gluing data is the same as maps from X to whatever the structure group is. So let's do this in terms of principal G bundles. If they're vector bundles, of course, I can make a principal G bundle. So you really just, for every point X in the middle here, I've got some way to identify the two sides of the trivialization. And by the way, we also know already that this is supposed to be the same as maps from, it would be now sigma X into BG. A little adjointness, standard maps from a product is the same as maps into the mapping space from one of the product factors. So this is loops BG. And what you find, and you can use a little Yoneda argument to that G is to prove this, that G is homotopy equivalent to loops on BG. So little advertisement for something to learn when you go further into principal bundles and a little bit of homotopy around them. What we say is that BG is a de-looping of G. because when I loop it, I get G. So BG is a de-looping of G. So in general, I can then, because S2 is suspension, I can think about the bundles on S2 as trivialized over the northern and southern hemispheres. And then I just need this, any bundle is, any oriented plane bundle or complex line bundle is going to be in one-to-one correspondence with a map from S1 to S1. And one of the first things we learn in algebraic topology is that there's a Z's worth of those. So for the tautological line bundle, I'm going to trivialize, so here we trivialize with, so, you know, you got this W in D2, and I'm going to look at the, this is actually sort of the, starting with the point in, around the point of infinity, all scalar multiples of the pair 1W. So this is sort of consistent over this disk. That's how I want to get this trivialization. And here I've got a Z and D2 and the scalar multiples of Z1. So that's a trivial bundle. And then you have to say, well, how does this go on the overlap if I, you know, Z equals W and they're both of that means they both must be of unit length, then of course Z1 is going to be equivalent to, I can divide 1 over Z, but that's of course the same as 1 Z bar. So the identification is through complex conjugation. And so what we're doing is we're mapping the way I'm going to look at say this is that Z is going to go to Z bar. And so that's degree -1. So with so we again see that somehow naturally there's a -1 here. By the way, an exercise, and this was a formative exercise for me when I first learned the theory of characteristic classes, is that for the tangent bundle of S2, the resulting map is degree 2. So again, the first Chern class of the tangent bundle of S2 is naturally sort of 2 times the generator, whereas the first Chern class of the tautological line bundle is -1 times the generator. Great. Okay, so now let's go and let's next talk about the associated sphere bundle for this wonderful little line bundle. So what is the sphere bundle explicitly? So all we're doing is taking the so the sphere bundle will be the units in each line, but the unit sphere, the natural metric to put on it, is just inherited from C2 on each line, in which case the unit vectors will be on the unit sphere. And so that's an S3 sitting inside C2. And that just maps to, well, its image in CP1. So this is a map from the 3 sphere to the 2 sphere. And yeah, so here's a basic fact. And by the way, this is a fiber bundle over every point in S2. I've got a sphere's worth. So this is called the Hump bundle. Again, it's just the sphere bundle and the tautological line bundle, but it has its own life in topology. So here's a basic fact. That if you have a fiber bundle, then there's a long exact sequence taking these two natural maps plus a connecting homomorphism from pi I of the fiber to pi I of the total space under the natural map, pi under the base of the natural map, and that there is a connecting homomorphism to pi I minus 1 of the fiber, and you keep on going. And so in this case, let's read off what happens. Let's just go around pi 3 of the fiber, pi 3 of S3, standard thing to prove. My favorite proof is through differential topology, is that's the integers, and it's just sort of the degree n map. You could just suspend the z go to z to the n map in the unit complex numbers. And then if I've got the identity map in here, then under the natural map, which is composition, then the identity map goes to the Hump map. And then we've got our connecting homomorphism to pi 2 of S1. And this is, in general, interesting, but I'm just going to cut it off here. Pi 3 of S1 is 0, because it's the same as pi 3 of the universal cover. Pi 2 of S1 is 0. So that means that this is an isomorphism. This is known to be Z, as we said, so this is Z, and it's generated by the Hump map. So when Hump found this, Doug Ravenel likes to say this sort of was like discovering the new world. The flat Earth theory was that homotopy was like homology, and homotopy groups would vanish above dimension. A nice property of homology, in various ways you can define dimension. In fact, one way you can then usefully define dimension is through vanishing of homology, especially local homology. But yeah, this is just the existence of this bundle and the long exact sequence of fibration says, fiber bundle says that pi 3 of S2 is not 0. In fact, there are many, many non-zero homotopy groups of S2. And by the way, they're all the same as those of S3, because if I take this little sequence and and go to the next thing, pi 4 of S1, et cetera, we'll see that pi 4 of S3 is the same as pi 4 of S2, et cetera. So pretty remarkable. So that's why I say this is, just as a map, is a pretty substantial thing. So another way, this will stick with the more homotopy theoretic viewpoint, is that that if we consider the standard CW structure CP2, then what you have is the 2 skeleton is CP1, and then I've got so CP2 is the same as CP1 union of 4 disk over some attaching map. So F is a map from S3 to S2, which is CP1. And what we find is that, and I'll give this as an exercise, F is the Hump Map. So there's a bit of geometry of CP2 to think about. You could think about, yeah, the normal bundle of CP1 and CP2 is an important thing to think about here. So I'll just leave that as an exercise. There's another construction. And let me first say that by way of contrast, I'm going to tell you about a different construction. So I'll get to the Hump map in a second, but let's another map. I'm going to take S3 and I'm going to make it as the union of D2 cross S1 and S1 cross D2. This is really, S3 is a boundary of D4, but if you apply the Leibniz rule to the fact that D4 is homeomorphic to D2 cross D2, you get this decomposition. So 3-dimensional space is sort of 2 tori, one that you can kind of see in front of you. And the fact is that if the universe were S3 and you drilled this torus out, what remains is a torus. It kind of sticks through here. So what we can do for this torus is, so this D2 cross S1, I'm going to map to S2 in the following way. I'm going to first take D2 mod quotient, each one mod its quotient cross S1. That's an identification. Of course, that's S2 cross S1. And then I'm going to project it. And similarly here. So this decomposition of S3 naturally maps to, because I've taken every point in the first torus and mapped it to the base point, and every point in the second torus and I've mapped it to the base point, what we really obtained here is a map from S3 to S2 wedge S2, and then I can just fold those two together, and that's a map, and it's got the name iota bracket iota. It's a Whitehead product. And by the way, there's nothing special about 2 dimensions here. Any even dimension, so more generally, say as an exercise, there's a similar map from S4m minus 1 to S2m for any m. So that's an interesting map from a 3-sphere to a 2-sphere. In the similar language, now let's talk about the Hump Map. The Hump Map is what you get when you instead of taking all the boundary to a point, you've got these two copies of the the torus, and so the preimage of this, the center of the disk, is going to be something that's kind of hitting the center of everything, but the preimage of something a little bit off is going to rotate around a little bit at a small angle until you get the preimage of something on the boundary is going to go sort of full around at like a 45-degree angle, and you can arrange for the same thing to happen on the other side. And again, I'm not going through the details here because this is equivalent to the Hump Map, so you can exercise if you want. Try to think about this decomposition of the 3-sphere and then how it's mapping to the 2 hemispheres of CP1 when you make it appropriately. So it's a very special. So the Whitehead product exists in any dimension, and the Hump Map really relies on the existence of the complex numbers in a serious way, one way or the other. Right. So let's. I think I'm gonna start calling it a day there. But then the final thing to say about the Hump Map geometrically is that the preimage of any 2 points are linked. You can find this yourself, and I think it's on a full YouTube, in which case I could do full screen, but I won't. And what you're doing here is often, he started with just 1 point and looking at its preimage under the Hump Map. Of course, 3-dimensional space that we live in is R3, but at a point in infinity, and you've got S3. So, and then he's representing the points in S2 down here. And so, for example, now you're fixing 1 point and looking at its preimage. And again, this is one of the most wonderfully twisted things that's actually been a word more than once when I've tried to explain what I do, what I'm interested in. It's you know, either I or the people I'm talking to say, "Oh, wow, that sounds twisted." And so here, you know, the more points in S2 you look at the preimages of, the more circles you get above those. You start seeing some of these tori, as I said, that last definition of the Hump Map. You see it more here. So yeah, I think I can stop there. And sort of let me then also say that Hopf detected this map is non-trivial in a couple different ways. One was to really geometrically look at these preimages, and the fact that they're linked would mean that under a homotopy, these we'll talk about this again. Under a homotopy, these preimages would have to unlink if the Hump Map were null, and so but they're all linked. So that's under concordance. I'll talk about that a little bit more when we do the Pontryagin tome construction. He also, you know, here's a quick thing you can say. If you believe that that it's the attaching map for CP2, then if it were null homotopic, then CP2 would be the same as S2 adjust 4, but it's not. Those stories are actually connected, but I don't think I'll I'll go through that